Well, let me tell you something about compasses. You take one out, you hold it level, and the needle swings around and points north. Always north. Never east, never west, always settling along that north-south line. And you might think, well, that is just what compasses do. But there is something deeper happening here. Something that explains not just compasses, but how magnets work, how atoms align, how the entire universe arranges itself. You see, that compass needle is doing what every system in nature tries to do. It is minimizing its energy. And that one principle, that simple idea, explains why magnets behave the way they do. Now, Earth has a magnetic field. You probably knew that. But what you might not have thought about is what that field actually looks like. Picture this. Deep inside Earth, about 3,000 miles down, there is a core of molten iron, spinning as the planet rotates. And that spinning molten metal creates electric currents. And those electric currents create a magnetic field. The field comes up out of the southern hemisphere, arcs through space around the planet, and goes back down into the northern hemisphere. It is like Earth itself is a giant bar magnet tilted about 11 degrees from the rotation axis. And here is something interesting. The field is not strong, not compared to what you might think. At Earth's surface, it ranges from about 25 to 65 microteslas. Now, a microtesla is a very small unit. To give you some sense of scale, a typical refrigerator magnet, the kind you stick notes to your fridge with, has a field strength of about 10 million nanoteslas. Do the conversion, and that is 10,000 microteslas. So Earth's field is, what, maybe 100 times weaker than a fridge magnet? Maybe 200 times weaker at some locations? Very weak. And yet, it is strong enough to swing that compass needle around every single time. Think about that. The reason the needle moves is because the needle itself is a magnet. It has a north pole and a south pole. And when you put a magnet in an external magnetic field, something happens. The field exerts a torque on the magnet. There is an equation for this if you want to be precise about it. The torque equals the magnetic moment of the needle times the strength of Earth's field times the sine of the angle between them. Physicists write it as tau equals mu b sine theta. But you do not need to worry about the math. What matters is this. That torque rotates the needle. It keeps rotating it until the needle lines up with Earth's field. And when the needle is lined up, when it is pointing north-south, the torque goes to zero. The needle stops. It has found the configuration where its energy is lowest. You see, a magnet in a magnetic field has potential energy, and that energy depends on the angle. When the magnet is parallel to the field, pointing north-south, the energy is at a minimum. It is written as U equals negative mu dot B, the dot product. Minimum energy. When the magnet is perpendicular to the field, pointing east-west, the energy is at a maximum. The magnet is fighting against the field, and nature does not like that. Nature does not like that. Nature likes low energy. So the needle swings north-south, settles there, and stays there. That is energy minimization in action. Now here is something you might not have thought about. Earth's magnetic field is not static. It moves. The North Magnetic Pole, the place where the field lines go straight down into the ground, is currently located at about 86 degrees north latitude, 142 degrees east longitude. That is up in the Arctic, north of Canada, out in the ocean. And it is moving. Right now, as of 2025, it is moving at about 36 kilometers per year. That is fast. Faster than it has moved in recorded history. Meanwhile, the South Magnetic Pole, down in Antarctica, is moving too, but slower. About 9 kilometers per year. The field is dynamic, it shifts, and nobody knows exactly why the North Pole is speeding up. But there is something even stranger. Earth's magnetic field has reversed, completely reversed. The North Magnetic Pole becomes the South Magnetic Pole, and vice versa. This has happened 183 times in the last 83 million years. We know this because of rocks. When lava cools and solidifies, little magnetic minerals inside the rock align with Earth's field at that moment and they lock in place. They become a record. Scientists can look at layers of rock, measure the magnetic alignment, and read the history of Earth's field. And what they find is that the field flips irregularly. Sometimes it flips every few 100,000 years. Sometimes it stays stable for millions of years. The last flip was about 770,000 years ago, which means statistically we are overdue. It could flip again any time in the next few thousand years. Nobody knows what causes the reversals. Nobody knows when the next one will happen. But here is the thing. During a reversal, the field does not just flip instantly. It weakens, it gets complicated, it might even split into multiple poles for a while. And during that time, Earth's protection from cosmic radiation is weaker. That could be a problem, but we keep looking. That is science. Now, let me tell you more about this energy minimization idea because it is not just compasses, it is everything. At the atomic level, magnetism comes from electrons. Electrons have a property called spin. It is not that they are actually spinning like a little ball, but they behave as if they have angular momentum. And that spin creates a tiny magnetic dipole. Each electron is like a microscopic magnet. In most materials, these little electron magnets point in random directions. They cancel each other out. No net magnetism. But in certain materials, iron, cobalt, nickel, the electron spins align. They all point the same way. And when billions and billions of atoms all have their spins aligned, you get a macroscopic magnet. A piece of iron that can attract other pieces of iron. A compass needle. And why do the spins align? Energy minimization. In ferromagnetic materials like iron, there is a quantum mechanical interaction between neighboring atoms. It is energetically favorable for the spins to point in the same direction. So they do. They form domains, little regions where all the spins are aligned, and if you put that piece of iron in an external magnetic field, the domains that are aligned with the field grow. The domains that are not aligned shrink. The whole piece of iron becomes magnetized, aligned with the external field. Lowest energy configuration. Now here is where people get confused. They say, well, if Earth is a magnet and the North Magnetic Pole is in the Arctic, then does not that mean the compass needle's North Pole is attracted to Earth's North Pole? And the answer is no, no, no. Opposite poles attract, like poles repel. The end of the compass needle that we call the North Pole is actually a magnetic South Pole. It is attracted to Earth's North Magnetic Pole, which is actually a magnetic South Pole. The naming is backwards. It is a historical accident. Early scientists named the end of the compass needle that points north the North Pole. But that end is attracted to the magnetic pole in the Arctic. And since opposite poles attract, the pole in the Arctic must be a magnetic South Pole, even though we call it the North Magnetic Pole. It is confusing. But that is how it is. So when you hold a compass, the needle's south pole is attracted north and the needle's north pole is attracted south. The needle lines up along the field lines, north-south. Minimum energy. Now, you might ask, why does the needle not point straight down or straight up? After all, Earth's field lines are not horizontal, they curve. Near the equator, they are mostly horizontal, but as you go toward the poles, they tilt. At the magnetic poles themselves, the field lines are vertical. Straight down at the north magnetic pole, straight up at the south magnetic pole. So why does a compass needle stay horizontal? Well, it does not actually. Not exactly. If you have a compass that is free to tilt, a dip needle, it will tilt to follow the field lines. Near the equator, it stays nearly horizontal. Near the poles, it tilts more and more. At the magnetic pole, it points straight down. But most compasses are designed to stay horizontal. They have a counterweight, or they are balanced in a way that keeps them level. So what you see is the horizontal component of the field, the north-south direction. And that is what matters for navigation. But here is something interesting. Magnetic field lines form closed loops. There are no magnetic monopoles. What does that mean? It means you cannot have an isolated North Pole or an isolated South Pole. Every magnet has both. If you take a bar magnet and break it in half, you do not get one North Pole and one South Pole. You get two smaller magnets, each with a North and a South Pole. Break those in half, same thing, all the way down to the atomic level. Magnetic field lines always form closed loops. They come out of the North Pole, curve around through space, go into the South Pole, and continue through the magnet back to the North Pole. Closed loops. This is different from electric fields. Electric fields can start on a positive charge and end on a negative charge. They do not have to loop back. But magnetic fields do. And this is because there are no magnetic monopoles. At least none have ever been found. Physicists have looked. Some theories predict they should exist, but nobody has ever detected one. So as far as we know, all magnetic fields form closed loops, and that has implications for how magnets interact. When you bring two magnets close together, their fields interact. If you line them up parallel, North Pole next to South Pole, axial alignment, they attract. The field lines connect smoothly. Low energy. If you line them up parallel but with the same poles next to each other, north next to north, they repel. The field lines push against each other. High energy. If you arrange them side by side, equatorial alignment, same poles facing, they also repel. The configurations with attractive force are the low energy configurations. The configurations with repulsive force are the high energy configurations, and magnets will move to minimize their energy. Now there is something else. The force between two magnets falls off with distance, but it falls off faster than you might expect. For two magnetic dipoles, the force goes as 1 over the distance to the fourth power. That is faster than gravity, which goes as 1 over distance squared. Faster than the electrostatic force, which also goes as 1 over distance squared. Magnetic dipole interactions are short range, very short range. Double the distance and the force drops by a factor of 16. That is why magnets need to be close to interact strongly. But even with that rapid fall off, Earth's field is enough. Even though the source of the field is 3,000 miles away, deep in the core, and even though the field at the surface is only 25 to 65 microteslas, it is still strong enough to exert a torque on a compass needle. That needle aligns. Every time. Now let me tell you about something that happened a long time ago. Scientists found ancient rocks in Greenland, some of the oldest rocks on Earth, about 3.7 billion years old. And embedded in those rocks are magnetic minerals, tiny crystals that formed when the rocks solidified. And those crystals are magnetized. They recorded the direction and strength of Earth's magnetic field 3.7 billion years ago. And you know what they found? The field strength back then was about 15 microteslas, comparable to the modern field, which averages around 30 microteslas. So Earth has had a magnetic field for at least 3.7 billion years, probably longer. And it has been roughly the same strength the whole time. Think about that. 3.7 billion years. That is most of Earth's history. The planet formed about 4.5 billion years ago. So within the first billion years, Earth already had a magnetic field, and it has kept that field ever since. Through countless reversals, through the rise and fall of continents, through the evolution of life. The field has been there, protecting the planet from solar wind, cosmic rays, charged particles streaming out from the sun. Without that field, Earth's atmosphere might have been stripped away long ago. Life as we know it might not exist. And all of that is happening because of the same principle that makes a compass needle point north: energy minimization. The molten iron in Earth's core is conducting electricity. The motion of that conducting fluid in Earth's magnetic field generates electric currents, and those currents produce more magnetic field. It is a dynamo, a self-sustaining cycle. The field maintains itself. The field maintains itself, and it does so in the configuration that minimizes the total energy of the system. Now, you might be wondering, is there anything practical about all this? Well, yes. Compasses, obviously. Humans have been using compasses for navigation for over 1,000 years. Chinese sailors were using them by the 11th century, European sailors by the 12th or 13th century. Before GPS, before radio, before any kind of electronic navigation, you had a compass and the stars. That was it, and the compass worked because of this energy minimization principle. But there are other applications too. Magnetic data storage. Hard drives. The data is stored as tiny magnetic domains on a spinning disk. Each domain is magnetized in one direction or the other, representing a 0 or a 1. The read head detects the direction of magnetization. The write head flips the magnetization to write new data. All of that relies on controlling the alignment of magnetic domains. Energy minimization at the nanoscale. Or consider magnetic resonance imaging, MRI. You lie inside a giant magnet. The magnet aligns the nuclear spins of hydrogen atoms in your body. Then radio waves flip some of those spins. When the spins flip back, they emit radio waves. The machine detects those waves and constructs an image. The whole process depends on the fact that nuclear spins, like electron spins, are magnetic dipoles, and they align with external fields to minimize energy. Or think about the aurora borealis, the northern lights. Charged particles from the sun, electrons and protons, stream toward Earth. When they hit Earth's magnetic field, they are deflected. The field channels them toward the poles. And when those particles hit the atmosphere, they excite atoms which emit light. Green, red, purple, shimmering curtains of light in the polar sky. That happens because Earth's magnetic field is there, shaped the way it is, channeling particles along the field lines. And those field lines exist because the system is minimizing its energy. You see, energy minimization is not just a principle, it is the principle. It governs everything, from the alignment of electron spins in a piece of iron, to the motion of molten metal in Earth's core, to the trajectory of a charged particle in the solar wind. Systems move toward lower energy, always. And when you understand that, you understand why a compass needle points north and not east. Now, I want to tell you one more thing. Earth's magnetic field is weird compared to the magnetic fields of other planets. Mars does not have a global magnetic field anymore. It used to billions of years ago. But the core cooled, the dynamo stopped, and the field disappeared. Now Mars has only localized crustal magnetic fields, remnants of the ancient field locked in magnetized rocks. Venus does not have a magnetic field either. It spins too slowly. The dynamo does not work without fast rotation. Mercury has a weak field. Jupiter has an enormous field, 14 times stronger than Earth's, because Jupiter is huge and has a lot of liquid metallic hydrogen in its interior. Saturn has a field too, but it is weirdly symmetric, almost perfectly aligned with the rotation axis. Nobody knows why. So Earth is special. Not unique, but special. The right size, the right rotation rate, the right internal structure to sustain a magnetic field for billions of years. And that field shaped the history of the planet, shaped the history of life. And it all comes back to energy. The universe arranging itself into the lowest energy configuration it can find. And here we are, standing on the surface of this planet, holding a little magnetized needle on a pivot, watching it swing north, and thinking we understand why. And we do, sort of. We understand the torque, we understand the energy, we understand the principle. But the deeper you look, the stranger it gets. Why does electron spin create magnetism? Well, that is quantum mechanics. Why does quantum mechanics work the way it does? Nobody knows. Why is the universe built such that systems minimize energy? Nobody knows. We can describe it, we can calculate it, we can use it to build compasses and MRI machines and predict the motion of charged particles. But we do not know why it is that way. And you know what? I think that is beautiful. We have figured out so much. We have taken this simple observation, a needle pointing north, and traced it all the way down to the behavior of electrons, all the way up to the structure of planetary magnetic fields, all the way out to the interaction of the solar wind with Earth's magnetosphere. We have connected it all. We have seen the pattern. Nature uses only the longest threads to weave her patterns. Each small piece of her fabric reveals the organization of the entire tapestry. But there are still threads we have not followed, still questions we cannot answer. Why is the north magnetic pole accelerating? When will the field reverse again? What happens during a reversal? Do magnetic monopoles exist somewhere, hidden in some corner of the universe we have not looked yet? What is the deepest reason that systems minimize energy? We do not know, not yet, but we keep looking. That is how physics is. You discover something beautiful, you understand it, you think you have it figured out, and then you find something you cannot explain, and you start looking again. So the next time you hold a compass, watch that needle, watch it swing, watch it swing, watch it settle. North-south, always north-south, never east-west. And remember what is happening. That needle is not just pointing toward the Arctic. It is obeying one of the most fundamental principles in all of physics. It is finding the lowest energy configuration. It is doing what every system in the universe does. It is minimizing, settling, aligning itself with the field, and in doing so, it is showing you something profound. The universe is not random, it is not chaotic, it has structure, it has order. And that order emerges from energy, from the simple fact that nature prefers certain configurations over others, prefers low energy over high energy, prefers alignment over misalignment. And that, I think, is beautiful that from one principle, this simple idea, you can explain so much. Compasses, magnets, atoms, planets, auroras, the history of Earth's magnetic field stretching back 3.7 billion years, the protection that field has given life on this planet, the way charged particles spiral along field lines, the way electron spins a line in a piece of iron, all of it connected, all of it following from energy minimization. That is how it works. That is science.